Alright, hello world. Welcome again. We have another problem. Gonna give a moment or two before we get into it. Yeah, so I've been kind of not working on these problems recently. I don't know, taking a bit of a break. I don't know, I'm all over the place. It's like, my thoughts are all over the place. That's the thing I've been struggling with. My mind is crazy. But there's like a couple priorities that I have right now that are kind of important, I guess. So I'm kind of heavily focusing on those things and not focusing on other things, but ultimately it's like, I don't know, I guess I'll figure it out. I'll figure it out as we go. Take it a day at a time. But yeah, let me go ahead and get into the problem. Get that going. So this problem is, we kind of already worked on this problem or thought about this problem. I have an idea. I'll explain it. So predict the winner on LeetCode. And do I have the chat? I do. Yeah. So you are given an integer array nums. The two players are playing a game with this array. Player 1 and player 2. Player 1 and player 2 take turns with player 1 starting first. Both players start the game with a score of 0 at each turn. The player takes one of the numbers from either end of the array, num0 or nums.length -1, which reduces the size of the array by 1. The player adds the chosen number to their score. The game ends when there are no more elements in the array. Return true if player 1 can win the game. If the scores of both players are equal, then player 1 is still the winner. And you should also return true. You may assume that both players are playing optimally. Alright, so this is an interesting program. So a few things to note. Because the set of numbers is relatively small, between 1 and 20, I believe this can be solved kind of directly, we'll say. So there's only a million, states to go through, a million possibilities. Yeah, only a million possibilities as far as, I guess you double it, it'd be like 2 million for the size of the tree, the nodes in the tree, so to speak. But my point here, the reason I bring that up is we can basically solve the whole game, and then the players can play with that knowledge. So it's, in some sense, a relatively easy question. Hopefully that makes sense. So what you can start with is you could say, all right, given whatever score player A has and whatever score player B has, let's say A is the first player, B is the second player, those scores only have three options. They could be equal, A could be greater than B, or A could be less than B. And they said that if A is equal to B, then A still wins. So A kind of has an advantage, right? The player who starts has a slight advantage, or so yeah, kind of an inherent advantage. What that means though is that every ending state, one of the player loses and one of the player wins. So every state is either a losing state or a winning state, depending on the perspective of the player that you're looking at, or at least every ending state is a losing state or a winning state for let's say for the player A. Now you can define inductively from the sort of bottom of the tree of possible states. You know, if you sort of consider a tree of possible decisions to bring you to another board state, of all the possible, from the leaves, all the parents could then be assigned either a losing or winning state if we assume that the players are playing optimally, because we can say the next player, or the previous player rather, has a choice. So let's say if it's player A that's getting to choose, and then player B is in a winning state or losing state at the end, or rather, if player A can choose a winning state for player A in any of its children, that makes that state a winning state for player A. If player B, if player A has no such decision choice, so all of the possible choices for player A, all those states are losing states for player A, then that makes that a losing state for player A. And we can actually go through the entire game from one player's perspective. We don't actually need to go through both players, because we only actually care about whether or not player A will win or lose. So yeah, we can just basically mark every node inductively as either, or recursively. You could do it recursively too. If any of the if any of the children nodes are winning children and obviously you can do that for the next parent and the next parent. I'm sorry. So if any of the children are winning for player A, then player A is in a winning state, and then for each of those children, you keep your repeat, and once you get down to the leaves, that's sort of the base case. And every leaf is either a winning state or a losing state. So you have that what do you call it? That invariant, I guess, is sort of true for every node that has children. So yeah, that's pretty much it. So I think it's pretty straightforward. Let's see if we can do this. Just do DFS. And yeah, we want to do depth first search, and we'll use a deck. We'll put the DQ, it's called, so we can push and pop elements on the left and right side relatively easily to restore state. And what we want to do is say, yeah, there are only two children actually at each step. So if either child returns true, then you return true. Otherwise return false. I think it's that simple. What do we do? Yeah, depth first search. Modify the state as you go. I think this is actually really that straightforward. Like I think it's actually that easy. Because you don't need to memorize anything. There's nothing to memorize. It's just yeah, I think it's like pretty straightforward, this question. What can we do? We want to integers, call it state, and we're gonna say we can do, I don't know if this works. Oops. And we're going to go ahead and say base case if state dot size equals 0. We're just going to have int A, int B, so initialize those both at 0. We're going to say return A greater than or equal to B. So if player A has greater or equal value to B, then return, yeah, there you go. Otherwise return, every case returns true or false, and we're going to say DFS, there are only two children for each node. So we would say, so state dot, so let's do left val equals dot front. Yeah, we can do both. Doesn't really matter. Well, it doesn't really matter. So okay, I'll do left val is deck dot front, which is actually state dot front. We'll come back to this in a minute if we need to. So there was state dot pop front, pop left, and then dff of A, B, and F, and this is going to be A. So player A can either choose the left side or the right side, and we do need to toggle between which player's perspective it is. We'll just say toggle. I think we need to do that. They don't have bool in C++. Oh no, they do. It's just not being highlighted. Okay. Yeah, so we'll toggle the player. So if toggle, then it's going to be it's going to be A plus left val, and otherwise, I don't know if I'm doing this correctly. B plus left val. And in every case we do not toggle, right? Toggle flips. Okay, and then we say yeah, we just say if. Terminate early. Okay, and then we do the same thing for the other side. Let's run state. So we're going to say state.push front of left val, and then right val. It's going to be state.back. I have to go check if these are correct. These deck operations. Again, we say toggle, and we'll do right val instead of left val. And we terminate early on any of these. And that's it. Super simple. Oh no, I'm sorry. Push back. Restore state. Yeah, so, sorry, almost missed that. So push back the left value, and then push back the right value, and push that back on. Yeah, and do this recursive, just a simple recursion. I think it's that simple. We just have 0, 0, and we'll do false for the which player? 0, 0, and the first player to go will be, excuse me, if toggle is true. So it starts off at true. All right, what do we get if we do this? What happens? How long did that take us to? 13 minutes. Wrong answer. Nice. Nice. Output true, should be false. Okay. Oh, it compiles and runs and everything, and it's wrong. Nice. Okay, well, sure. Really? Okay. So if A can win, that means take the left side, we pop 1, and left A plus 1 is 1, and B is 0. Our next toggle is now false, so we have 1, 0. The next one we pop 5 for the second player, and that's 1, 5. Really, so one of these, oh, okay, interesting. What are all the possibilities? How does this happen? I want to get the tree of things that are happening. Why does it feel like this is not correct? Oh, I'm sorry. Yeah, no. What are we doing? If you pop the left value, you add it to A if we're true, add it to B if we're false. And then push back the left value, get the right value, pop that. If we're A, we add it here. If we're B, we add it there. And then if it's true, we cascade upwards that true value. So apparently player 1 can win. So I think I'm wrong about with my logic here. So player 1 can win if he picks 1. If player 1 picks 1, if player 2 picks 2, and player 1 picks 5. Right? I think the issue I'm having is we need, depending on the toggle, actually the toggle matters a lot. Yeah, actually that matters a lot. Okay, that's what I'm doing wrong. Okay, so if we're looking from the perspective of, yeah, I get it now. I have the right idea. The code completely changes in both cases depending on what toggle says. Okay, so if toggle is on, we get the left state pop, and then we're gonna say we're looking from the we're looking from the perspective, so we want to know, is this a winning state for player A? If any of the children are winning states for player A, then we return true, right? So, yeah, so if we recurse and we get true on the left side, so we can kind of somewhat disregard this other piece. We're gonna come back to this in a moment. Hold on. Yeah, so we get rid of, we don't even care about this other part. So we say that, restore the state. Now we operate on the right side, pop, and we say toggle, we already know toggle is true at this point, and we are not going to even touch the left side, the other side. All right, now restore the state. Okay. So these two different executions. Now what's interesting is that's from the perspective of the first player. Otherwise, we have kind of a mirrored thing that happens. Oh, this is no. Right, okay. Now, what's interesting about this is if we get true, if we don't get true and true, that means we return false here. This other side is going to be very similar. And we're actually going to go ahead and okay. Yeah, this is an interesting question. I think this still works, but we definitely want to do this properly here. Also, definitely over, how are we doing? 20 minutes, okay. Over 20 minutes, all right, fair enough. So now, if we're on the perspective of the other player, right? Now we're only adding to the B, player B, And it's not, we're not terminating early anymore. In order to return, so from the other perspective, player B, if in order for this to be a winning, to return true, for it to be a winning position for player A, it has to be a losing position for player B, which means if any of the other positions return true, then we actually return. Oh, this is so confusing. I think I did this wrong. I don't know. I think it's hard. I think I did it wrong. Like the logic is a lot easier if you kind of use two players, I guess. But so is this a winning position for player A? Yeah. See, that's the confusing thing. It's like it's not player A's position. I think that's what's confusing is that this isn't player A's turn, so you wouldn't say that this is a winning or losing position for player A. Really, this is, yeah. So this function basically needs to say if it's a win. It really has 4 return types, I guess. It's a winning position for A, or a losing position for A, and a winning position for B or a losing position for B. Because of the perspective, right? That's super confusing. Yeah, I don't know. I think it still works though. I think it's still okay. So from here, if player B okay, so you look at your player B's perspective. If player B wins, then that means player A lost, right? So everything's kind of inverted here, but it's also saying if any of these children return false, right? If any of these children return false, then player B can take that child, and this is going to return false. But if none of those children return false, that means that we should return true. Yeah, super confusing. It's actually, depending on the toggle, right, you have different logic. But that's kind of the point. But I don't know. I don't know if this is correct though. I think the issue is like this is too confusing to implement correctly. Also is not right. Nice. How do I do it correctly then? Still got true. Yeah. Okay, it's wrong. So let's try it this way. 4 states. Winning position for A. Is it on A's turn or B's turn or whoever's turn? Like that's the thing I'm kind of getting hung up on. From the perspective of the player, is this a winning position or a losing position, right? Depending on who goes last. There are all these leaf nodes where A has a score, B has a score, and then basically all of the positions have been taken. And you have a pair of booleans for like player A is winning, player B is losing. Winning, yeah, because there really are two values, right? Like there's only a toggle between player A wins and player B loses, or player A loses and player B wins. So you really could just do a Boolean, like player A wins or loses. From this position, that's what this function can be. But the thing that's tricky about it is, so basically player A wins is what this function is going to check. And we'll say from player A's perspective, choosing the left or the right, right? If the left child, the right child, if player A wins from the left position or the right position, then we turn true. But if player A doesn't win on either of those, then this is a player doesn't win. Okay, it's simple enough. But then now, if we're from player B's perspective, we say, okay, if player A wins on the left side, then player A still wins. I actually think it feels like the logic was correct the first time, which is so confusing to me. I don't know. I'm kind of confused now. If player B makes a move and on the left side player A wins, then this is still a winning position for player A. And if on the right side player A still wins, then this is a winning position for player A. Otherwise, yeah, I don't know. I don't know what happened here. How did we... This is actually what I had before. This is wrong though. What? Okay. All right. Hi, friends. I'm good. How are you? Hey, what's up, Melito? Welcome back. Hello, hello. Welcome. Why does it feel like... I feel like I checked this 5 minutes ago. I didn't realize it. All is well. All is well. I'm struggling with this question though. I thought this was relatively easy, and here I am, not able to solve it. So there's that. That's where I'm at right now. I'm just kind of wondering, what did I do? What did I do? Excuse me. I think what I want to do is, for each call, I'm actually going to call a routine after each of these calls. So we'll do a let's do it this way. Let's do bool check. I can try to get a better sense of what's happening here, so maybe I can figure out what am I doing wrong in my thinking? Because I think this should work. That's why I'm a little bit uncertain. Not if check. We'll just do... Yeah, we do if check. That's fine. We're gonna say debug for const auto brilliant. In state, we're going to say check. And we're going to say standard cout x. Yeah, we actually don't need this part. Okay. Does that come up at all? So with 3 elements, we should have 2 raised to the third. We should have 8 different paths. And that's interesting that Here's the state before we check it. Okay. I want to print the state and then what value we get when we check that state. I actually need to do this before you pop. Okay. And I think that's also interesting is that you can do this actually at the top up here, but you don't necessarily know if it's true or false that you get. Right? It's only after you get the check that you know which one's which. So we're gonna do that for each of these. This is a little bit more involved than I would like it to be. It's kind of a lot of like copied code just to get the just to get the debug messages where I want them to be. You have to kind of transform everything here. Before you pop the front, before you pop the back. And here we have a similar thing again, check. It's going to be equal to this guy. And I want to say, all right, how does this look? Compile error. Oh yeah, because we redefined check a few times here. Yeah, we could reuse the same variable, it's fine. Actually, just define it once in each scope. All right, what do we get? What does this look like? So 152.522. This is supposed to happen before check. Okay. What do we get here? That's not supposed to happen. 152.52.52. So what happened is this debug gets called. We don't necessarily know. Excuse me. Trying to figure out for each node what its I basically want like a memoization function of like the state, the value for the left side and the right side, those values, the state, all of that sort of encoded into one key, and then whether or not it's true or false. Yeah, I want to know what the function parameters were when we returned true or false. What the state was before this was called. Maybe I'm doing this wrong. Maybe it should be like. Let's do it this way. Make that a copy, and then we do it like that. Instead of the state, use temp. So now, yeah. But we also want what A was. And what B was. And the values. Excuse me. Okay, let's try that. That's probably better. Probably better. So we'll take a copy of the state before we execute a routine. Definitely not the most obvious things here. Also, you gotta take the state before we is that after we pop or before we pop? Yeah, I think it's after you pop. Yeah, right before you call the function. That's where you want to save that. Hopefully I didn't confuse everything here. So that's hopefully the what you would call the copy assignment operator. So it would copy the state in this temp variable. And then the temp variable will stay on the stack after everything gets called and be available later. So once we get this value, we can print everything that was in the state when we called A, B, and these values. All right, what happens if we do this? Okay, it's a little bit better. A1, B5, vals empty. Nice. You're kidding, really? You serious? Oh, I guess that makes sense. Yeah, that's the first thing it's printed. So yeah, these print after the code is executed. So actually you're going to see all of the leaves get printed first. So 1, 5, vals, check 0. So that doesn't make a lot of sense to me because excuse me. Oh, actually it does make sense. Yeah, it's before you pop the value. It's after you pop the value. Oops. So this should then actually be the state before you pop the value, I think. I guess, I don't really know. Also, having this duplicated code here is kind of awkward. Because it's not necessarily consistent across all 4 of these different spots that we're calling this. Like, I kind of would like to somehow wrap this, but I'm struggling to comprehend exactly how. So there you go, 152, 152, 1052, and also we don't need this extra value here. Or extra space. Right, doing that 4 times is really awkward. Like I said, I don't know necessarily what this code should look like, so I'm kind of struggling with like how to debug this exactly. But all right, we're at 40 minutes now. Oof, oof. So 152 check 0. So not a winning state for A. Which is what we expect. 152 not a winning state for A. 1052 not a winning state for A because B chooses 5, right? And then A can only choose 2, so that's not a winning state. A1, B5. Now how come we don't have A2 anywhere here? That's the first thing. And the second thing is, so A1, so as we expect that. So A1, B5, vals 5. I don't know where that came from. That's not correct. But somehow A can win that one. And A1, B0, vals 5, 2, A can win that one as well, which is not true. So both of these are not true. And then this one, so this is where the problem is, right? A0, B0. Yeah, okay, so that's the issue. All right, and this terminates early, so that's why we don't see A picking 2 at all. Okay, I get it. Right, so this is wrong. How did we get A1, B5, vals 5? What happened there? Let's see. I think I'm pushing and popping things incorrectly. That must be it. So state front, left value, pop front, a left value, push front, right value is back, pop back, push back, it's right value, a plus right value. Okay. Then we have the left value is B is going to select, so left value is the front, pop the front, push the front on the left value, and then we select for B, toggle, B is plus the left value, push that left value back on the front, right value is the back, pop the back, push the back at the right value, there we go, that's supposed to be right value. That may have been the problem all along. That may have been the problem all along. Still wrong though. So, okay, 152 makes sense, 152 makes sense, 1052 makes sense, 1251. So A picks 1, B picks 2, A picks 5, and wins. A picks 1, B could pick. So I guess that's the thing, is that this isn't right though. Just because this is a winning state for A, so B shouldn't pick 2, basically, right? So this is also kind of an issue. Excuse me. Because yeah, so the logic does change depending on the player, right? It has to be, if it's player B's perspective, it has to be every choice returns true in order to return true, right? So we're gonna say just bool any or bool. It's actually the other way around. It should be. Yeah, I think I had it right the first time. Or not the first time, but I had the right idea. Where if it's if that child node is a losing node for player A, that makes this node a losing node for player A. Yeah, so not check returns false. I think I had the logic correct before, but I didn't have the. And then if we make it through, then we return true. I think I had the logic correct before or something, but I just didn't have that. I copied I copied the function incorrectly. Wrong, still wrong. Ah, why is it so hard? Why is it so hard to code? What is this? There's logic to get it correctly. It's basically a brute force solution. Like, it should be fine, but it's just I can't get it right. Can't get it right, man. Okay, let's try again. So what's wrong now? Somehow we have 1, 2 as the values. It should be 1, 1, 2, 5 or 1, 5, 2. What happened here now? What happened here now? Oh, I think you need to push. Yeah. Okay, I think I see the issue. I think you need to return the state before you return. Let's try that. That might be the issue. And the reason why you need to do that is that you need to check the other branches. Yeah. It's a little bit awkward. So we have the check and have this state. Before we do the check, we do push back right, and then here push back left value. At this point, I'm going really slowly because I'm just trying to get the logic correct, which I'm actually not really sure if I have that correct at this point. And then I can clean up the code. There we go. Now it's right. Okay. So, all right. So we go through all the possibilities. We say, okay, 0, 0, 1, 5, 2. We could pick A goes to the right, and now B hasn't picked yet, and we have 1, 5. Then we could say B goes to the right, and we have 1 left, and then from those possibilities, we can. Now, what's interesting is we don't. Yeah, when well, right. So it's clear. It's clear if we go to the right for A. If we pick if B picks 5, then we lose, right? Because A can only pick 1 after that. If B picks 5, now I don't know why there's 2 of these. I don't know what happened here. A to the right picks 2. B could pick either 1 or 5. B could pick 1, in which case A wins. B could pick. Yeah, see, there's 2 of these. I don't know where there's 2 of these. Where'd that come from? I don't know why that is. Why would there be 2? A goes to the right. He picked 2. B is 0. Vowels is 1, 5. B goes to the right. You have vowels of 1 left. A is 2. B is 5. Vowels of 1 is left. From there, it's A's turn. Oh, I see, because A could pick the left side or the right side. That's why. Yeah. It's the same value. It's 1 both times, but it could be from the left or from the right for A. So that's why you get 2 printouts. Because it's false in both cases, right? Yeah, so it's just okay. So this will both give you false. So this is false, so we don't return true, and then we call it again, and yeah, okay, that's why. We get 2 printouts for 2 zeros. That makes sense. It's pretty interesting. So then we pick A, B, 1, 5. We go back here. Print that out again. You could pick. Okay. Oh yeah. So if A goes to the right and B goes to the left, then A wins, right? And I guess there isn't much printout for that for whatever reason. I don't really know why that is exactly. Couldn't tell you that either. That's kind of weird, but yeah. So if A goes to the right, there is a possibility for A to win, but B can just pick 5, and then that's that. If A goes to the left, right, so if we're back here again, A goes to the left, B can go to the left, and that's what we have here. And we don't even bother going to see if you can. Oh, I see why. That's why. Because as soon as we figure out that A can win, at some point we could terminate early. So that's kind of what's going on there. Okay, so I think this is correct. Let me try a bunch of other test cases. Let's get rid of the debug statements. We're gonna just comment everything out. But there are some problems here. This took a really long time to code, and there are a bunch of things to say about this that are. First, I just want to see if it's correct. We'll start with that, and then we'll kind of refine our thoughts a little bit here. There's some things to consider. There are some things to consider. Okay, is this still correct? Did I comment anything out I wasn't supposed to comment out? I can comment out the state too. Okay, gotta wait a few seconds. Actually, that was, I think, what caused the problem. Okay, so I think we're right. Let's try a bunch of different test cases now. These numbers are relatively 10 to the 7th is pretty big. I think it's 10 million. 1, 2, 3, 4, 5, 6, something like that. Let's try some random things. Is there going to be at least one? Yeah, there's at least one. And the values have to be at least, they could be 0, yeah. Probably write some awk scripts to generate some random test cases. Have my Sigwin terminal over here. It's pretty neat. Pretty nifty. Yeah, you can kind of tinker. So, like if I wanted to write, let's do, like if we want to just generate all of those, let's do it this way, I less than or equal to 20. And we're going to say s plus equals s dot I. We actually want with a comma, right? Do 19, and then at the end, I want to do I, comma. What does this look like? So this is the 4. Okay. Oh, yeah. Interesting. Syntax error. S20. How about this? How do I create a string out of? You actually want, like, you could do like that. There we go. That's what we want. Okay. You can maybe do this. That might be the way to do it. There we go. That's what we're after. Yeah, I was saying before that you can write a quick awk script instead of typing all these characters and then just copy paste. Might be a better way to do this than that too. Let's do it. Try to do this in one for loop. Let's actually do, yeah, let's do like this kind of a thing. And we actually don't need to have an end either. We can just do print s, I think. Yeah. Don't need this ending part. And we can do I, comma space. That's the problem, is that we'll have this space at the end. We could do if I is less than 20, then we'll do s equals s with a comma. There we go. I like that. We also could do plus equals, right? No, cannot. So that's the confusing part. How about this? No. Yeah, gotta have the string concatenation there. I like that awk script. That's pretty good. And we give spaces in between too. There we go. Not bad. So anyway, probably could submit this, I think, at this point. I think this is correct. Let's try it and see what happens. Let's go for it. I don't know if this is correct. Just kind of guessing. Oh, that's right. Got there. Okay. Great. So we have the basic idea. I had the right idea, I think, initially. I think I coded it incorrectly. Let me see if we could try again. So if toggle is on, then we have these two we have these calls. Right, part of the problem is if you return true before you pop. So okay, let's get rid of all this stuff in between. Let's get rid of all these things. All the debug code, the print statements, all the extra noise here. It's gonna break this down to, or narrow this down to like the core of what's happening here. So I think part of the issue that I had before was that we terminated too soon. We were supposed to we were supposed to restore the state after the call before we evaluate. I think that was the problem, because I think I was okay before with the toggle, the if-else toggle, being sort of in each of these, I guess, setting the check. So you would say, yeah, so this is basically the same code. You pop and push and evaluate, and if you're toggle, then you would evaluate. You would add to the B value. If not toggle, then you add to the A value. So let me see if I can write this in a way that's not an if-else, but sort of works differently. Let's say handles both cases. Oops. I guess handles both cases. So you would say, okay, if this Boolean check is going to be, so we'll do toggle times that, I think, left value. And same deal here. Where toggle could be an integer, we could actually just make it, well, it's an integer type, it's fine. So toggle being 0, we don't add a, right? So it's actually do false. So false means the first player is going. Actually, wow. If toggle is true, we add to A. That means that A is going. Yeah, that makes sense. Okay, let's do it that way. So we'll do toggle times the value, and then here it's 0, and when you toggle, it'll be the other side. So then you push, you pop, push, check, and then now if toggle is true, and the check, then you return true. If toggle is not true, then that's really confusing. You do not check, return false. That seems to be the correct thing to do. So if toggle is false, then you say and it's not true, then you return false. Yeah, so that's super interesting. And obviously this sort of guards. And then you say, so that's the left value. Push front, push left, and then do your check. And then the right value is a similar thing. So you do toggle times right value times the right value, push back the right value, and you do the same check over here. If toggle is true and check is true, return true. If toggle is false. And I think in both cases, yeah, so you'd return, so here this is not toggle, and here this is not toggle. So you return not toggle. Okay. And this, I think, in theory, will be faster because you don't have the this branch statement. It's quite the function we got going on here. It's wrong. Of course, it's wrong. Of course, it's wrong. Oh man. So pop, push, pop, evaluate, push, pop, evaluate, push. Toggle and the check is true, return true. And if the toggle is false and check is false, return false. And you return not toggle, whatever we have going on here. And this doesn't work. And it's not right. Really. If toggle is 0, that means we're looking at player B. That means we would add, right? And if so not true, return true. And we'd be in this case, right? Return false, if not check, return false. We wouldn't even evaluate the other side of the tree. If toggle is true, if toggle is 1, then we're looking at player A. And that's my mistake. I didn't really think about this. It's a not toggle, yeah. Whoops. That's not embarrassing, but that's a mistake. There we go. All right. Is this still correct? Let's see. We'll find out. I don't know if this is still right. There we go. Yeah. This is quite the program, though. This is like, I don't know about this. I don't know about this one. Huh. Very interesting approach. Do we need the toggle? That's a good question. Good question. Do we even need that? Also wondering if I can make this one statement. Toggle and check return true. Not toggle and not check. So both of these could just be toggle. That's the first thing. And then we got to make this expression the same. So it's if toggle is equal to check. Yeah. Right? Because if it's not toggle and not check, they're both false, then you return false. If they're toggle and they're check, they're both true, they return true. So if they're equal to each other, return what that value is. There you go. I like that. That's a fun one. Alright, let's give that a shot. Let's see if we can... Okay, still correct. Shaved a millisecond off here by removing that. Now the question is... Yeah, I mean... It's kind of the best that I got here. I don't think I can do much better than that as far as like keeping the code terse. I think that's all I got. Only 25%. It's kind of interesting. It's not the most efficient. I don't know what's more efficient. I mean, maybe there's a way to do this that's like greedy. It's a faster way. So pretty interesting question. We could check the discussion. I feel like I'm gonna get schooled if we check the discussion though. We will do that. Yeah, I mean, this is what I was thinking. It's just it was hard to kind of get it right. I think the if toggle not toggle approach is better, like to code it quickly, but noting that you need to evaluate the check after you restore the state, I think is important. I think that's something I missed. It's an important lesson. Yeah, I mean, obviously you copy this code gets copied a few times. You know what you can do, well, no, never mind. I was gonna say maybe there's like a way to evaluate this differently where you can make this a single function that you call, but actually part of the problem is that these routines themselves are sort of they're sort of part of this. Like even though you're doing the same thing both times with the value that you grab, it's this push in the back, pop from the front with the deck is like kind of the right way to do it, I guess, something like that. I'm not really sure how to express it. But anyway, so yeah, I think you can make this a little bit faster if you don't use a deck and you use integers I and j. So you could do it that way, or integers left and right. That's easier. So left val is state of left, and then you say, not even state of left, it's now nums of left, and you say left plus equals 1, and then 2 left minus equals 1. You actually don't want to do minus equals 1 if you can help it. You actually want to do, well, actually that's fine. I think it's okay. greater than or equal to right. And the same thing, you can do num's right. Right minus equals 1. Oops. Right plus equals 1. How about that? How about that? That might be a little bit faster. Let's see. Oh! Ouch. Ouch. Really? Oof, wrong answer. 15246. Now that's really interesting. It's faster, but it's wrong now. Now why is that? Oh, no. I think it's actually got to be this way. I think you need to actually, yeah. You miss something important if you do equals. They have to be past each other, these two. So that's quite a bit faster. Still only 30%, but definitely faster. Now my question is, can we do, depending on toggle, you pick between the left and the right. Not the toggle, but the, so that's great that this is fast and correct, but can we do better than this? 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 Seems like we can. This is pretty simple code, and I like this. I prefer this over the deck. Cannot quite make this its own function yet, though. Actually, you can. Are you ready for this? Can we inline? Well, you would get the same thing, but you can do auto func, call it, or eval child. So this is going to have access to everything. Now this is actually going to be an int reference, call it which. Oh, but this is plus minus minus plus. Shoot. Int direction. This actually would just slow things down, but you can do like, okay, interesting. To do int val. Now this isn't really good, but I want to try this. So you can do int val, nums of which. Now you do val is equal to itself, and then it's going to be plus direction times, yeah, well, plus the direction, and then minus the direction. So minus equals direction, plus equals direction. Right, now this is a reference, so you're actually going to update which, no, not val. And then now you have this which over here. Yeah. And now you can call oh. Hmm. Oh no, what's interesting about this though is that this return value doesn't really make as much sense anymore because of depends on the toggle whether or not you terminate early. So oh no. You actually need this check. It doesn't work really well. It doesn't work that well. You just put this at the end of each eval child, but never mind. It's too much. It's too much extra effort to do all that. These are very similar to each other. These functions. Pretty interesting. 8 milliseconds. Really? Can we do faster than that? What's the discussion? Someone must have done this really fast. But yeah, I mean, the basic idea is the same. It's just, it's a depth first search where you pick either, depending on the player, you can pick the left or the right side. And so you need to include a toggle. You have two evaluations, left and right. In theory, you could have like kind of an evaluate children function, but like I said, it's kind of to these parameters, this left and right parameter, like being able to cycle correctly through the possible states. You gotta set that up correctly, properly. But anyway, so once you've done that, then depending on which player you are, your evaluations change. That toggle, like we really would have like I said, you have 4 different kind of pieces here where you can say left and right for the first player and then left and right for the second player. So this would be sort of copied 4 times. I think the part that I missed that they made this take a lot longer is resetting the state, getting the check, the running your recursive check and then resetting the state afterward before terminating early, which is a little bit confusing, but the reason for that is that it's not really terminating early as much as it is cascading the values upwards. And obviously, yeah, there's a little bit of the early termination. But I think I want to say something like the discussion, the discussion probably you could do it linear time complexity, dynamic programming, quadratic time, linear space, recursive solution, quadratic MIT OCW solution explanation. Interesting. DP. Force top-down DP. Why would you do DP on this though? That doesn't seem to make a lot of sense. Recursive solution explanation, DP of memoization. Memorization. Memoization. Memoize. Is it actually memorization or memoization? I always thought it was memoize, not memorize. Should be memorization. Is this just like a sick joke? It's called memoize instead of memorize. Never hadn't noticed that until now. Alright, let's see this one. Minimax game. If you went to MIT and took 6.046. Everyone can see this explanation. Okay, great. Wow. Quite the open courseware. Oh, that's what it is. Okay. I actually didn't think you could do a memoized solution on this. Okay, so it's util v I d p I j. I know you certainly can do dynamic programming solution on the left and right values, like left, right, I and j, or left, right, a and b. Certainly you can do that. That's relatively straightforward. dp of ij equals max ab. What is going on here? What is going on here? Okay. If num size modulo 2 equals 0, return true. Okay, so there's an even number of value. So just out the gate, this is like, what? Serious? Hello? How'd you figure that? Excuse me? If there's an even number of values, you just immediately win the game. Why? Why would that be the case? What do you mean? Huh? Someone explain that to me. Wow. Where does that come from? Does anyone explain that? Your solution does not work. Oof. Oof. Ouch. Ouch. Is this correct? Only described a linear strategy for solving the problem. The size of the problem is even for good reason. The size of the problem is odd. Question is harder. The odd size problem could be decomposed this way. Either the first player. I was gonna say I don't have 1, 2, 3, 4, 5, 6, 7 test case I could fail. Ooh. Whew. got him. So this isn't even correct. All right, I was gonna say I don't think this doesn't make sense to me. Whatever's going on here. Max score, player gain for any subarray. I get the feeling this question only has a few test cases, and you can just solve for all the test cases, and then you have a quick answer. Score gap between player 1 and player 2. Max of nums, TP nums. Gets more. Can reach the formula by noticing it is a min-max problem. Player 2 gains points, player 1 loses them. Excuse me. Brilliant is brilliant is brilliant. I don't know if this is good or not. But it's interesting that it's, yeah, quadratic time. My solution's not too great, huh? Not the best. Not the best. Why so slow? Min-max problem. Well, I mean, the DP part we can do a partial DP, certainly. You can do like this. Although this isn't really. Oh, I see. Okay, you can do, this is better. Well, okay, let's do it this way. There's a left, right, A, and B. Key is going to be equal to A greater than equal to B. And return that. And everywhere where you return, it's going to be the same thing. Oops. All right. How do we do? Compile error. Nice. Compile error. Compile error. Compiler error. Okay, got it. Oh. Map to a Boolean. All right. It's still correct. So this is also a dynamic programming solution. This actually, this is quadratic, believe it or not. This not the form that I have it in here, but there is a quadratic version of this. Yeah, okay. This is a lot slower though. Wow, that's a lot slower. Interesting. So yeah, I'll explain momentarily what this looks like. Okay, so we can get rid of one variable, the a variable. We can use x instead of a. And I'll show you what that looks like shortly. Oh, no. Yeah, instead of a and b, we have x. Get rid of one integer. I'll show you why. Because this is the minimax, right? So we can actually just have one sum that we increment or decrement depending on what we're adding. So yes. So x greater than or equal to 0 is what we want now instead of a and b. And then we say left value, right? So now we would say instead of a and b in our toggle, we just have x, and it's going to be, so it's either, so if we're toggle is whether or not is actually going to be plus or minus, so 2 times toggle minus 1. So we want to go 0, 1 to mapped to negative 1, 1. So if it's 1, and so we subtract 1, yeah, so we go 2 times toggle minus 1. And this is if we're player 1, then we add the value to x. If we're player 2, 0, then we would subtract this value, right? And now that's what we're going to do for x. So we have the same function over here. And this is x instead of a. We can get rid of b altogether. So you don't actually need to optimize this question because of because the values that they're asking, one from 1 to 20, it's small enough where you don't actually need to get too crazy with this. You don't actually need the dynamic programming solution. Let me see if this works. Let's see what happens. Compiler error. Okay. Thought I missed something. There was something I was sure there was something I missed. Okay. Is this still correct on all the test cases? Maybe, maybe not. Find out shortly. Okay, still right. Okay, so now we've memoized on 3 variables instead of 4. And by the way, we don't necessarily need to memorize everything. We can actually comment all that out and see how fast it is. It's probably still pretty quick without all the memoization. Excuse me. Because it's not inexpensive to memorize things. It's not free, so it's definitely quite a bit of memory being used to memorize, or definitely memory and I guess cycles. Now let's keep the memoization. Now what you can do is you can go even further and say, actually the left and the right. I'm actually not sure now. This doesn't speed things up at all, though. Not really. Doesn't really speed things up very much. Fastest we had so far was 8 milliseconds. I think part of the issue with the left and right is I'm actually not sure about that one. I want to say you can just pick an integer, but I think you do need to go over all those possibilities, like moving. Yeah. Like there might be multiple ways to get to a certain point score differential between sort of the left and right. Like, yeah, you've sort of DQ'd a certain amount on the left, DQ'd a certain amount on the right, and there's a bunch of different ways that can happen where you get the same point score, but whatever state you're at that point doesn't matter, because the game is going to be the same from that point on for all of those different possibilities. So you save a little bit of computation using DP here. But yeah, I mean, I guess the upshot is that you can use DP on this program to this is a lot more efficient asymptotically than what we had before. What we had before was actually exponential in the input, O of n, so it's 2 raised to the n, it's O of 2 raised to the n. This is a lot faster. This is now, it was O of n to the fourth when we had a memoization of fourth. Technically O of n to the fourth log n, but you could modify this to use hash map. Use a hash map, and then in that case it would be you can modify this to use a hash map, and then in which case it would then be O of n to the fourth rather than O of n log n. But I'm kind of lazy at writing the hash function over and over in C++. I tend not to do that. So this would be, yeah, you could do O of n to the fourth memoization, and then you could modify the A and B values to just collapse that to an X value, just one differential that you care about. And then you'd have, then you're looking at excuse me, O of n cubed, because you have different left and right possibilities. I don't think this is a minimax problem, or no, it is a minimax problem. I'm sorry. But the thing about it is, there's apparently a way to optimize this using dynamic programming which is kind of what I'm doing here, but to exclude certain possibilities altogether, I guess. And that's, I think, the thing that I'm kind of getting stuck on. It's like, how do you cut out yet one more dimension here? How do you cut out one of these variables, the left and right variables? Because you don't necessarily know when you would pick the right side or when you would pick the left side. I want to say that's probably where the minimax comes into play, or slightly more optimized, is that you know that the players are not going to pick a side. I guess you could say, like, you could DQ all the way from left to right and just assume that each player is like, I mean, maybe the way to consider it is like, because I want to say something like you could sort the array first, right? Because you know the players are only going to pick the largest values they could pick each time. And every time they both have an option between two values. So they're both going to be as greedy as possible, sort of. Now, you might not want to be that greedy because you might want to not pick the larger value, like not let your opponent pick a larger value that's coming after, in which case you pick a smaller value. I don't know, can you argue that you're just always greedy? And then in which case then, I think that's kind of, I don't know, it's kind of hard. It's kind of hard. I don't know. I guess this being a minimax problem, you can go from the bottom up, so to speak, and start with the last value that was chosen. And I guess it depends if you're even or odd. Tells you whether or not this is a positive or negative value. And then you have a choice of picking something to the left or to the right from there. And so I guess you kind of have like a, from each starting point, like which element you'd pick next, so to speak, kind of a thing. You have sort of a sequence to the top, just sort of optimal for, I guess that's what they're getting at. So you'd start at any spot and sort of grow out to the left or to the right, grow out to the end. And each time you would try to optimize for the first player. Well, the first, each choice you would try to pick. I don't know if every choice is greedy though. That's the thing. I'm kind of not sure about. Like, I don't know about this. This is like not the most obvious thing. I definitely see the cubic dynamic programming solution. I get that, but I don't see the quadratic dynamic programming solution. That one I don't see. Struggling with that one. One line, huh? Not the most readable solution, just for fun, for the sake of being able to put a logic in one line. Very clear, not that unreadable. It's fine. Add a cache. S and E. Assuming the sum of the array is sum, eventually player 1 and player 2 will split the sum between themselves. Player 1 to win, she has to get more than what player 2 gets. If we think from the perspective of one player, then when he or she gains each time as a plus, if the other player gains each time as a minus, eventually player 1 can have greater than positive total, player 1 can win. Simulate this process in each round. If E is equal to S, there's no choice. Have to select the nums of S. Otherwise, this current player has two options. Helper, select from the front item, leaving behind the choice from the tail, custom E-1, and take the max of these two options as this player's selection, return it. Okay. Yeah. Oh, I think I see the problem. Oh, this is actually um really. Wait, what? Wait a second, wait a second. Why is this one so much easier? How come I don't know, how come I'm missing this? This is my solution. We don't necessarily need to hold on to this. Hold on. Something's wrong here. Something's not right. I'm confused about, but let's see what we can do. So left, right, we can do the tuple left and right, and we're gonna have an integer, excuse me, that will memoize, and this is just gonna be left and right. So we have our key, our left and our right. We're going to memoize. We don't have anything there that we set that. Left is greater than right. Then key equals. Well, actually, hold on. Yeah, so it's not going to be DFS anymore. Let's get back to we'll do the memoization later. Actually, we'll do that another point. So the suggestion is actually the left and right are sure, I guess. It's not a DFS anymore. It's something else entirely. Okay. I don't know, I guess it's a kind of DFS. I'm not really sure what to call it. So we'll say return standard max of, we'll say int left, select left. And the tricky thing is you do need to know which player it is, though. So we do still need a toggle of some kind. So we'll say left greater than or equal to right. We'll say return. Said 2 times the toggle minus 1 times nums of left, we'll say, right? So select left. So this is a little bit confusing. You're going to add I think I understand. So let's do select left and select right. Take the maximum of those two. Select left, we're going to say, int, we're going to say sine, 2 times toggle minus 1. So we recurse on F with left. We select left, left plus 1, right is untouched, toggle is flipped, F is the same, and you'd say sine times this value, nums of left plus, and select right is going to be same thing, the right side with a value plus left doesn't change, right decrements by 1. And eventually they meet, right? You're never going to have a situation where you're moving too far. Yeah, because like you're not going to go off the edge, because left will eventually meet right if you hit that point. Okay. So select the left side, select the right side, take the maximum of the left and the right, and then you say return DFS it's greater than or equal to 0, something like this. Okay, wrong. I want to say if it's the first player, so true, you add this value. Yeah, first player true should be greater than or equal to 0. Oh, yeah, greater than or equal to 0 should be true. False. Great. What happened? What's wrong? Select left, select right, take the maximum of the left and the right. It's 1, 5, and 2. Okay, first select the left side, you take 1, and then you recurse on 5 and 2. The right side, you pick 2, recurse on 1 and 5, take the maximum of those two possibilities. So if we recurse on, take the left side and say, oh, so actually, if this is the, oh, that's interesting. So, yeah, actually want to do this way. Want to do it this way. If toggle, then return maximum. Otherwise, return the minimum. So I guess this is sort of why it's minimax, I guess. It's a kind of minimax question. that might be what I'm doing wrong. Not sure. It might be. Let's see. Where are all those test cases that we had before? Let's just go for it. I don't know. I don't want to go through find all these test cases. I'm kind of trying to go through this somewhat quickly, I guess. Oh, it's correct. Really expensive, but correct. Whoa. That is not optimized at all. That is okay. Interesting. Wow. Why is this one so slow? The other one was so fast. It's only a few milliseconds, even though the other one was exponential time. That's super strange. I wasn't expecting that. Interesting. I don't know. Yeah. Well, this one could be memoized. Yeah. So why this is correct is like I guess this is kind of simple. This is an example of a minimax question. So your function gets a score, and yeah, I think the reason why this one is more expensive is because this is exponential, and when you have the toggle in there, it's even more exponential, something like that. I don't know. It's another exponent added, or another multiplication added. But my point, or I guess what I want to say is, so your function is going to be a score, which is player one's score. It's not going to be true or false anymore. It's actually going to be the score itself. And that's our return value. And then we're going to say take a for our player, we can either for player A, we want to maximize our possibilities. So we either select the left or select the right, and we're going to say playing optimally, we're going to pick the maximum of the left or the right. For the other player playing optimally, they want to pick the minimum of the left and the right. Right? They want to minimize the other player's score. So we're going to flip between each of these selections, and performing the selection is it's going to be take the left value and add that to the function that we so the tricky thing here is like so we take the left value. When we select the left, we select the side, we take that value and we add it to what's left over, I guess the function operating on what's left over. However, we also have to consider which player we're playing as, because if we take a value as the first player, then we want to add that value to the sum. If we take a value as the second player, we want to remove that value from the sum. So that's it. I mean, that's what's going on. It's pretty straightforward. Using this toggle, but wondering if there's a better way to do this with the toggle. Also, yeah, there is a DP way to do this. So let's use memoization, right? Let's do that. So actually, it's going to be int bool, believe it or not. So not quite. It's more or less quadratic, but it's got an extra piece to it, which is interesting. And if we already have the key, then we are going to set that. Otherwise, we say memo of left equals of key equals this function. Okay, what do we get if we do this? Is this still correct? Let's find out. Hey, oh, that's fast. Oh, that's very fast. That's a lot faster memoized. There you go. There you go. That is super fast. And I think that logarithmic factor maybe plays in. It's a lot faster. This is quadratic. The other one, by the way, we did just a moment ago was actually exponential. But now this is quadratic. This is super fast. It's much faster. And you can use dynamic programming to do this and kind of go backwards. So you would do. The thing that's weird is the dp of ij. So let's even do. Oh, get a phone call. Get to that. Come back to that in a moment. There's another way to do this, which would be, so this is what other folks already had. And we're going to say dp, and we're going to say of, we're going to do n, we'll do n, yeah. N of vectors of size n, 0 size n, or yeah, n 0. I think the count comes first with vectors, vector constructors, count value, okay. And what we're going to do is we're going to initialize from the bottom. So I guess we'll do I equals 0, I is less than n, plus I. Notice this is positive 1, negative 1, right? At each step. So we can say our initial, so dp of 0 of I, excuse me, is going to be plus or minus, we're going to have a toggle also, so we'll do sine, start off, so when left equals right, you add depending on the toggle. So I guess you don't necessarily know who's going first at each point. That's kind of a tricky thing, man. I don't know. My thinking was that like, well, we can get the sine of the leaf node, and then also that's kind of interesting that you add or subtract that value. Yeah, well, it's going to be. I don't know, the toggling makes things really awkward. Toggling makes things pretty awkward. Who is the last player to go? See, that's the question, right? Because you can figure that out, right? Because if there's 5 elements, first player, second player, first player, second player, first player, right? So the first, so it's all they're all the last. Yeah, so that's interesting. The sign is going to be n modulo 2. If it's so it's either 1 or negative 1, right? If there's 4 elements, it's first player, second player, first player, second player. So it's negative 1 if they're even, and positive 1 if they're odd. You do sine times and basically we assume for each of these we ended on these values, right? So it's going to be nums of I, right? So that's the first row. Then we're going to say the next row is, again, it depends on whether this is even or odd, but the next row would be the opposite sign. And it's well, I guess it depends on the sign, but the next row is going to be either the minimum or the maximum of the selecting left or selecting right. And you obviously, if you're on the leftmost side or the rightmost side, you can only select left or only select right. And your sign flips as well. Well, it depends on the sign. And when you select, you're going to add your things both multiplied by the sign. So yeah, it's a little bit funky, but you're going to say dp of basically I plus 1. So it's going to be something, this will be a double for loop here. J equals 1, we'll say. Well, yeah, we do I. There's an outer loop and an inner loop. I kind of want the inner loop to match this I, but that's fine. It doesn't have to. It doesn't have to. Also, today is the 25th. Today's Wednesday. Okay. So this is kind of interesting too. So this will be if the sign is less than 0, otherwise, and we toggle our sign each time. So sign equals make a one-time sign. Okay. Yeah. So if it starts off negative, then we go to positive, and positive means and the sign is never 0, so it's either 0 or greater than 0. It's either negative or positive. If it's positive, we want dp of j I, and this is, yeah. So the rows are going to be j, or I rather. Rows are going to be I. Column will be j, and this is going to be equal to. So if the sign is positive, we want the maximum of adding the left and adding the right. Well, the sign multiplies. So there's a select left and a select right for j. That depends on the sign. So so this next line is going to be that's if you can select left also. There's only really two options, so there's either left or right, which means, let's say if we go to the middle, there's left or right, which means, excuse me. Again, the sign flips, but it's the left is j minus 1, so it's dp of I minus 1, j minus 1. And the right sine times dp of I minus 1, j plus 1. Okay. But selecting those values is you're going to add these to I minus 1j. You have to handle the edge cases too. Yeah, so that's select left, that's select right, and then if the sign is positive, then you're taking the maximum of select left and select right, and if it's the sign is the other direction, then you're actually going to take the minimum. Now, the thing to note about this is like super awkward because look at how much like finagling with this that I'm doing, like how much thinking and messing around. Like this would take forever if you had to code this up like this in an interview. This would be an eternity. Can be done, I guess, in theory, but you'd have to be like pretty well prepared to be able to do this correctly. Yeah, so then that gives you I guess the best possible at each layer, right? So the second layer, either pick the left or the right, and this is really confusing too, because the second layer means that you picked two elements and you either said, okay, I'm going to of those possibilities, in some cases there's two. I don't think this is going to work out correctly. I don't think this logic works. I've done this before where I start coding something and it actually doesn't make sense. Before you select the last value, the other player has really only one option. It's either the left or the right that they could have picked. Right, which is, yeah, that's what we're doing. We're saying it's either the left or the right. And we're sort of considering each of those cases where that's the best possible outcome for the player at that point. The player who's, yeah, so it's maximizing for the player that's sort of currently selecting. What that means now, could have come from the left, could have come from the right to get to this point. What I'm wondering is, this is something of a triangle also. Because you can't actually pick a left or a right. If you're on this is very confusing. if you're on the leftmost side, if you're j equals 0, then you can't pick a left side. You can only pick a right side. It doesn't really make a lot of sense though, the way that I'm trying to do this. Because going like bottom up doesn't really seem to make a lot of sense. Top down is okay, but bottom up doesn't seem to make much sense. I think I and j have to be the left and right values. I think you have to reverse this. So yeah, so actually someone had this before where they had this is actually a diagonal where they're equal, where all the values are equal. Yeah, and then because here this left, it's going to be, so if this is a diagonal, then this actually is going to be diagonal -1 to go to the left on the I, and then diagonal +1 on the right. Yeah, that's kind of interesting. So select left is actually like we're going backwards now. So this number, it's actually nums of to go. So that's so confusing. I don't know. Oh boy. Oh, who knows now? Let's say, I don't know, let's just say we look at this portion alone, just this part. Let's not look at the loop yet. Figure that out later. Let's say that sign does toggle. Okay. So we're saying we're going backwards here, right? So we start off I is here. This is the left is equal to right. So adding 1 is going to get you to the diagonal. So subtracting 1 means you're looking at sine times nums of, it's going to be I is the left, so left -1, and then that is, yeah, I guess it would be dp of I, we'll say, I guess. And then the other side is you're subtracting 1 from the right. It means you add 1 to the right, so you have nums of j plus 1. We're saying I and I, so really this is ij, I guess. That would be the left selection, that would be the right selection. and we're actually going to set this. Now it's not the diagonal anymore though. I don't know where we're storing this value though. I don't know what we're doing with this. This return value is what? Where do we store this? Well, I want to say this is the, I guess our new DP value. I don't know. That's very confusing. I don't know where these things go. I don't know. I don't know. Well, at the bottom of this tree, you go left, 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 left over and over again. And eventually you get down to just this value. And you come up and you go right, and then you say, depending on the toggle, you're going to, it's sort of like a tree, either select left or select right. You have a left and a right, and you take either the maximum or the minimum of these two values. And that becomes that tree's value. Just like a DP. Yeah, I want to say it's so confusing. It's so confusing. Yeah, okay. Yes, no, we had it right the first time, I think. So, oh, I'm kind of getting tripped up for some reason here. All right, so these should be what I was suggesting before. This should be actually just 0, right? That'll be sort of the bottom layer, I guess. I guess we can go backwards too, but that's fine. It doesn't matter. We can do it this way. So the bottom layer will be each of these values, and then the next layer above it will be we're going to add at each point. We're going to say take the value on the left and the value on the right, and take either the minimum or the maximum depending on what the sign is. So that'll be I and I minus, so it'll be I minus 1, and J, now what's interesting is it's actually going to be so when you get down to these values all the way at the bottom, these function calls where the left and the right are equal, the thing that calls these two functions, the parent node calls the left and the right. So I think that's kind of interesting. It's not exactly a tree. So you have the left, you have the right, they're equal. The deal is there are two things that point to that node. I want to say something like this is sort of like it's like a two-dimensional tree or something. Like, I don't know. I don't really know how to express it. It's kind of hard to wrap your brain around it. But what I want to say is I don't think this is a linear time algorithm, even though at the end we have all of these different left and right values. The left and right are equal to each other. So there's only n values to consider at the bottom. I think I don't know, I gotta think about this. So there's some, I guess there's some number above, right? So when you get to the select left and select right, part of the problem is that you can remove the left value to push towards that one value on the right, or you can remove the right value to push towards that one value on the left. And in both of those cases, you would add this value, and you consider both of those. I don't think I have the right idea doing this. Setting dp of ij, dp of 1, like what should go in dp of like 1 0, for instance? Like what's that supposed to, or 1 1 even is probably better. Well, 1 0. What's that supposed to represent? Well, that's going to be the sum of two values, right? But which two values and why? It would have to be, the only selection you can make is the right side. You can't make a left side selection because when j is 0 already, subtracting 1 goes to, so it's something like this. So the left side would be j minus 1, the right side would be j plus 1. And you are selecting nums of that. Yeah. Now, is that totally correct? So that doesn't seem right either. But let's think about that. I don't know, man. I'm stuck on this. This is like, I don't know. I'm struggling here. I'm struggling. Yeah, because I don't know what the next layer is supposed to be. I thought I had it for a moment, but I can't really get it. It's supposed to be backing up here. Like you just back up. So you just go. Okay, you have to add some nums left or nums right. So it looks like at each point we're going to add a nums value, but I think the issue is we need to know what value of j we select. So the second layer, I think, is going to be all the possible sums where one value is negative, the other one is positive, but all the possible selections of size and yeah, consecutive sums of length 2. I think it's all the consecutive sums of length 2, right? I think that's ultimately what we're going for here. These are the not exactly. I mean, because the way that you add this stuff, like all the there's all they're not just the consecutive sums. This is really challenging. I don't know. I'm really struggling to go backwards. I want to say it's relatively easy, but I don't think it is. Also, it'd be nice if I could find a way to I think if I hash this with a memoization function, like unordered map, this will be faster. That would be good. But like I said, I think it's even faster if we just use a DP solution. But the problem is I'm trying to understand, like, how do we even set this up properly? I get that there's the toggle in there that, or the sign that changes whether it's max or min, and also changes how you calculate these things. But how do we go backwards, right? Because we're now we're adding nums of left, nums of right, but these left and right values are they represent something different than what this represents. This is like each layer, these I and j, they're not actually the left and right values anymore. So we're kind of memoizing on something different now. And this layer is when they're equal. When they're not equal, then the layer before or the layer after, however you want to look at it, that is, depending on the sign, either the minimum or the maximum of adding one of these. These are both values from the previous layer, right? So dp of, this is sort of the left and the right. How do we figure that out, the left and the right? Well, let's say j is left and j plus 1 is right. I mean, we could do that. So if j is 0, then the right one would be on the right side. Actually, if j is 0, it really should be minus. This should really be the left one, and this should be the right decision. Because there is no left to choose on. Yeah, there is no left element to choose when you look at j0, which is confusing. Because you already picked the left element, basically. There's only the right side you can pick at that point. Whereas if j is 1, you can go left or right to select to get to j is 1. And, excuse me, and I'm just so confused now again. This means, by the way, I think this means that j has to be where I is also. And you're going to add to the right. It's going to be like a triangle. And so selecting the left and selecting the right for j of 1. That is so confusing. I'm just so confused. Yeah, I don't know. I don't know what I'm doing here. We'll just say 0. Yeah, because this is kind of like a tree. I could draw the function call. Like the function call tree is relatively straightforward, right? Like there's the top node, and then there's 2 choices, left and right, and then from each of those nodes have 2 more, and there's 2 more and 2 more. So it just keeps, tree just gets bigger and bigger. What makes this memoized is that some of the selection parts of the tree actually overlap with each other. So when you memoize it, it's a lot more efficient. And I want to say the tree becomes more like a triangle. So the first call has a select left and a select right. And then each of those calls have a left and a right and a left and a right. And where do they overlap though? They overlap where left and right are equal, because there's an optimal value there. And that's kind of the issue I'm having here. I probably could go the other way around. I probably could go top down. And, well, it really is bottom up, but the problem with the top down would be and it's interesting too when you get calls, you think like it might be spam or might be something important, like you can never tell. So you're always like, oh, I gotta go check and see who called. Excuse me. You can't really go top down because there's a few problems here. Like you can't really go top down because you don't know what the previous layer was or is. You can do it recursive. That's what we did. This is the top down version. But the bottom up version, we have the bottom, we just don't know how to produce the next layer. We don't have the inductive step. That's actually the issue that I'm having here. I'm trying to figure out the induction part. What the next, if we knew what the previous layer was, what do we do with what do we have for the next layer? I think it's like, I guess you would call, like if you only had 2 numbers, right, or 3 numbers, you only had 3 numbers, right? This top part, you would have a left and select the left element or the right element, and then each of those only have 2 numbers, and there's an optimal sort of value for those 2 numbers, depending on if you're left or if you're which player you are. And then, oh, that's kind of interesting too. There are 2 different arrays here to consider. There's the optimal for player 1 and there's optimal for player 2. But I think the interesting part is that yeah, that's kind of the part of the memoization, that you can actually end up in the same left and right position. I think that's one of the things that's tripping me up, is that this is not a 2D array exactly. It's 2 2D arrays. 2 of them. One of them for the first player, the other one for the other player. I think that's what's really tripping me up. Or one of the things. This doesn't have like a direct mapping the way that I would like it to. Because in my mind, I'm thinking like, this is like, why is this so hard? Yeah. I think this toggle, though, I think this really is just like a mechanical thing. I don't think you necessarily need to memorize the Boolean part. I actually think we can get rid of that. Let's do that. Let's see what happens if we do that. I don't think that's necessary. Also, I think I need to get rid of this code. I mean, I get rid of it, but it's fine. It compiles. Yeah, okay, I'm wrong. That was not tripping me up at all. That was perfectly fine. No, it's not tripping me up at all. I just am struggling. Yeah, it's just a strictly mechanical thing, so I don't really care who the player is. So it really is just one array then. Okay, that's fine. So, okay, yeah, we want to consider like 3 elements and 2 elements and 1 element. So 1 element, base case, no problem, right? Depends on the sign. 2 elements, we would, if we pick the left side, then we have a right base case. If we pick the right side, we have a left base case. So let's do it that way. So there's a left side and there's a right side. Let's say the left side. For some element j, which is going to be, so we are going to go with j to n minus 1, or n minus I, right? We don't need to go through, we don't have to go that far because, I guess left to right, because it's going to be kind of like a triangle, right? Just each layer is going to get smaller until we get to the top. So we did j n minus 1 minus I. We could pick, so with 2 elements, it's either the left value we select, we'll say j, and that means that we have to add our dp of the next layer, which is the previous layer, and that's going to be, we select the left, so we have 2 elements, we select the left, means that we do j plus 1. If we select the right, that means we do the other side. J. Yeah. If we select the right element, that means the left element is the one that we have to pick for our DP. Okay. That's super confusing. That's like not obvious at all, but that seems to be how you go from, that's how the interplay between 1 element and 2 elements is that our 2 element selections, there are 2 possibilities for each value of like what you could select, what's left over. There are n minus 1 of these like 2 selections, right? And whatever you pick, the left side or the right side, that DP is the other one is the DP that you have to that you'd optimize it with. So yeah, so that I think that's the way to do it. And then depending on your sign, you would say for this J, it's going to be so actually, yeah, you don't need to check anything with regard to like bounds checks. You could just do j plus 1 because you have n minus I, so you'll always be able to access that j plus 1, and so your ij is going to be just the maximum or the minimum of those selections, depending on whether if the sign is positive, you want to maximize because you're from the perspective of, and this is just really if you're dealing with, it's really just a toggle, and it really just matters initially if you're even or odd number of elements. But if your sign is positive, then you're from the perspective of the first player, and you want to maximize. If your sign is negative at that point, then you're from the perspective of the other player you want to minimize. And I think that's it. I think this is the recursive step. It should be the same at each step. So once you get to now, you're going to 2 and 3 elements. Same deal. That for 2 elements, there's the left and the right, and there are these sort of I guess sequences of consecutive 3 elements, and there's obviously n-2 of those, and each of those can go to each one can go to 2 different n-2 or 2 element consecutive elements, and the best for whichever player is sort of I guess dominates that layer will already be stored in the DP, and so it's only going to be either you're going to add the left element, and you're going to say that just got added, so now we're going to append that to the DP of the 2 elements on the right, however we got that, or you're going to select the right element from your position, and then you're going to say the other 2 elements we calculated previously from the left side. This is really confusing. I don't know if this is correct. This doesn't seem right, because to me it seems like if you add j over is equals 0, it feels like you could add j equals 0 over and over again, and you shouldn't be able to do that. You shouldn't be able to add, well, I don't know, like, yeah, I guess this definitely doesn't feel right. Because you can get that select left, and it feels like you're adding, not necessarily, so you don't necessarily add I guess that's maybe, I don't think this is correct. It's kind of confusing. It seems like it seems like you could add, it seems like when j is 0, you're looking to decide between adding j or j plus 1 over n more than n times. So if you did this four loops of this, that means you would have had to have added j is 0 or j is 1 multiple times, which is a little bit confusing. I don't know if that's correct. That doesn't seem right to me. Don't think that's correct. That does not seem correct. Yeah, it definitely doesn't seem right. Interesting. I want to say, actually this is supposed to be also a DP value. It's not. I don't think so. No. It seems like it, but these are calculated in different ways, I think. Yeah, this is not the same as this. It's very tempting to, this might be DP actually. No, I don't think so. I don't actually know, like, what are these supposed to store? That's the thing, it's like from 2 to 1 or 1 to 2, it kind of makes sense. Like you would have two values to j and j plus 1, and the second layer is this sum, and you either pick the left side or the right side to get to that DP state, or this is so confusing. This is so hard. I don't think I'm doing this right. I don't think so. I think I'm doing this wrong. I want to memorize the tree. That's what I'm trying to do. There's a tree, there's a function tree. I think I need to draw the tree. I need to draw the tree to get it, get the idea. So you have L, R from the top, and then those have functions, function calls, and then those have function calls. Right, and this is, what do we say? This is L plus 1's R minus 1, okay. L plus 1, oh. And then this is R minus 1. And then these are the same, right? This is L plus 1, R minus 1, and this is L plus 1, R minus 1, right? So these overlap. And these are, this is L, R minus 2, and then L plus 2, R. Okay. And then this has two values, and these overlap. And see, this is why I need more practice, and specifically more practice with dynamic programming, because these overlap now. And you see that there's 1, 2, 3, 4 nodes, right, at each level. There's n nodes at each level. And these are, which is L plus 1, so this is L plus 2, L plus 2, R minus 1, right, L plus 1, R minus 1, L plus 2, R minus 1, or L plus 1, R minus 2, it's here, right, and that's L plus 1, R minus 2, and this is L, R minus 2, R minus 3, and this is L plus 3, R, right? So there's this kind of value that you're shifting from left to right. So these are also, right, and that just keeps happening. It just keeps going, right? And you end up with quadratic a number of nodes altogether in the tree. That's all well and good, that's fine from the top down, but how do you go bottom up? How do you go, well, the bottom up clearly is L plus N R to L plus N minus I R plus I to L it's actually minus I. And it's not really N, it's, well, all the way on the left side, basically L becomes N. And L starts off at 0, too, by the way. L is 0, and R is basically n, more or less n. So this is L plus n minus I to R minus I to L R minus n, which is exactly, if we had to like kind of write out these values, this would be n to n minus I to 0, 0. So that is a little bit confusing, but yeah, this is actually a diagonal on your DP, sort of. But then, so if you just replace L and R with 0 and n, we'd be in great shape, right? This would be, so this is n to 0, 0, and all of the values in between. And then above it is what? It's n minus 1, right? N minus 1, oops, so nn. Above that we have n minus 1 n, right? To R minus 3 is what? L of R minus 3, 0 to n minus 3, right? It's not n minus 1, it's actually, oh, yeah, n minus 1, yeah, or, which is n, excuse me, yeah, n minus 1, right, no, it's n minus 1, or n, zero, 0, and then this becomes, I think it's n minus I minus 1. R is n and L is 0, right? So this goes to 0, 1, which then becomes n minus 2, n, m minus I minus 2, m minus I to 2, which looks like you have, it's confusing as all heck, but you get n minus j, n goes to n minus I minus j of n minus I, which then goes to 0 to j. That's what the yeah, that's what this I guess if this is the sort of values of your matrix, this is sort of what they look like. This is what each layer looks like. So when j is 0, excuse me, when j is n, you have 0 n, or yeah, at the top, you have 0 n, and then you have, when j is 1, n minus 1 n, and 0, 1. Or no, j is n minus 1, excuse me. When j is n, it's just 0, n. When j is n minus 1, this is 1, and this is 0, n minus 1. Yeah, which is exactly correct, right? 1n, 0, n minus 1. Okay. Right. So let's say we want dp of 0n, right? Let's let I be 0 and n be j's n. Then this is related to, depending on the sign, of, this is quite the picture, quite the matrix, quite the thing going on here. Definitely a lot easier to think about if you do this with just memorize the recursive function and call it a day. Super easy that way. Otherwise, this is like translating this is just a headache. Because it's just a hash map, so it's a super straightforward translation, but you had to kind of figure it out. It's like, yeah, it looks like you're going, this is the bottom of the array, which is kind of unusual. So actually, yeah, you would initialize like this. This is your I. Yeah, your I is 0. This isn't actually the base case when I is 0. So your bottom row, and the bottom of the triangle is actually the middle of the matrix, right? It's actually the the diagonal is all of those values, and then you actually are going to build diagonal after diagonal. That's actually what you end up doing. You build the diagonals out of the bottom parts, which is very confusing. That is very confusing. And 0 and all right. So let's build this matrix, and let's try to program this. I would like to translate it somewhat where this is actually the bottom, but I don't actually know how. I think it's too confusing. Try to do that. But yeah, so these feed upward, quote unquote upwards. So okay, I'll try to program each of these, what this looks like. But this is only related to one value. This depends only on one. This is only going to be used to calculate one value. Well, it's the other way around. It's actually this uses these two values. So okay, so let's try to do this properly. But yeah, definitely need the picture to see that correctly. So yeah, I was right that it's I and I, and it's basically n and n are when left is 0 or left is all the way to the left. It's actually reversed too. So n represents L plus n. Yeah, that's also confusing, but yeah, this is sort of reversed where nn is the left moving to the right, and the right moving to the left is yeah. So it's actually like I said, it's confusing. It's really confusing. Okay, let's try to understand this. So we're going to ultimately return dp of n minus 1, n minus 1. And another question is, yeah, these are actually supposed to be n. I used n, but it's really n minus 1. This is the last index value, so it really should be n minus 1 here, not n. That's okay. So yeah, and it's actually going to be O0 n minus 1, and we're going to say start from the bottom, which we said I, right? No, yeah, the bottom is actually a diagonal, and then we're going to do perform on each diagonal from there. So now we subtract 1 on the left value. So our for loop is going to be, we'll have this inner, we'll do j. And we went from left to right, so we can do that again. So left to right, also left to right, will be 1, 0. Let's do I for the inner loop. There's going to be this value 1, or I minus 1, I guess. Something like that, however we do this. So I is still going to range from n minus 1. So it's going to be from 0. This I is going to range from 0 to n minus 1. I kind of already know what this looks like. This is going to be a j here outside. I'm not sure what j is going to look like exactly, but basically there's this value that affects I. So this is like this is like a DP problem that we're setting each of the diagonals, which is really unusual, really interesting. Not typically what I do. So j will be 1. So you do n minus j, right? And so j is 1. You're going to go from 0 to I is 0 to n minus j. And this value is going to go, it's going to be I plus this j, and there's I plus j. 1. And we're going to say the row is 0 at the top. So j, that's i's, yeah, so that's I, goes from 0, and then this is I plus j, right? So here j is 1, I plus j, at the end j is n. It's really n minus 1, but n. Right, when j is n minus 1, we do I of 0 to n minus 1 is 1, so I is less than 1, so it just executes once. And say I to I plus j is going to be equal to, now we're going to use these two values, which is dp of, it's going to be related to dp of one thing and dp of the other thing. This is, so what's the relationship? It's L r minus 3 is related to L plus 1 r minus 3 and L r minus 3 r minus 4. So or alternatively, this to the thing that comes before it, which is 1, 1. So 0, 1, which is I plus j, is related to dp of 1, 1 and dp of 0, 0, which is 0, 0 is I. And this is, it looks like I plus 1, I plus 1, something like that. And how are they related to these things? And this is 0, 2 would be related to 0, 1 and 1, 2. So this part is the same on both of these. Or rather, yeah, this part is j. This is j and j minus 1 is the right sides. And j minus 1 has the same I, it looks like. Yeah, so it looks like I and j minus 1 and I plus 1 and j, right? So they're on the same diagonal, basically. They're diagonally apart from each other, these two values. Yeah, we're making a triangle to the right. So the two values are, one is below and one is to the left. And so they're diagonal across from each other. So yeah, d of I is the row, and the column is going to be I plus j. And actually it's a diagonal also. It's just the plus j tells you how far up the diagonal is. We're moving diagonally, and then each of those diagonals are using two values that are also on another diagonal. Just the diagonal that they're on is, so it's not j, it's this I plus j diagonal. It's this one is to the left and one is down. So you take I plus j, and to the left is you subtract This is such a tricky thing, man. This is like so awkward. Subtract 1 to go to the left, and then don't subtract 1 and subtract 1 here to go down. Yeah, that's what we got. But that doesn't really make sense. I don't think that really makes sense. So, excuse me. This O2 at the end here, 0, and yeah, it was all reversed too. This is so, oh man, okay, anyway. So row 0, j is, 2. For 0, 2, we're going to say that depends on 1, 2, and 0, 1. So 0, j is 2. This won't work, right? Because, so this, or rather, yeah. You subtract 1 on 0, 2 is j, right? I plus j is 2. Subtract 1 to 0, 1. But you add 1 over here, which is so weird. I plus 1. dp of I plus, does that even exist? How does that? It's making my brain hurt. So supposedly this will already exist, this 1, 2, before we get to 0, 2 here. I think I need to like write out a little bit more about what this looks like, because this is just it's making my head hurt. Take a nap too. Okay. Let's do like with 4, right? At the top we have 0, 4. Then we have, we said 1, 4, 0, 3. Then we have 2, 4. 1, 3 it looks like. And then 0, 2. And then 3, 4, 2, 3, 1. You just decrement both, right, by 1. And then 1, 2, and 0, 1. And finally you have 4, 4, 3, 3, 2, 2, 1, 1, 0, 0. Yeah, this is absurdly confusing. But I kind of get it. Like, it makes sense. It's just like makes your head hurt. So this depends on 1, 1 and 0, 0. These depend in this way. This is so the next layer is related to the previous layer by this relationship. So, and I'm not sure what to put here, quite frankly. There's some j, I guess. J equals 0, we'll say. J equals 1 up to j equals, looks like 4, or n. Could say n minus 1 really is what it should be. So j loops from 1 to n minus 1. Or 0 to n minus 1. Well, yeah, I mean, actually it should be 1 because we already set that appropriately. And the next thing is, yeah, so this layer is what we're trying to figure out now. And that's going to have we want to go up from 0, 1 to 1, 2. So we really just add I. I just loops from 1 to, or yeah, well, 0 to something minus j. This is n minus 1 minus j. Or yeah, just like that. That's all. Just add I. That's all. It's really just adding I to everything. Okay, and what are these things? It really is 0. So 0 plus I on the left side. And then the right side looks like j plus I. Yeah, j is 1. Okay, that looks fine. Then what they depend on is, whoops. Oh boy. Get confused. What they depend on is one of these things you decrement j and leave I. One of these, to the right side, you decrement j and leave I. And the other one is you leave j and increment I. So you leave j and you increment I. And that seems really confusing because we're used to looping not over diagonals but over vectors. So this I plus 1 will actually exist, j plus I will actually exist, believe it or not. Yeah, just so confusing, but it will exist. And yes. Mm-hmm. So 0, 1 will be 1, 1, and 1, 1 will exist. Yep. Yes, sir. Yep. That's how it works. And how are these related? Well, there's select left, select right. So let's write those. Int select left. Oops. And we're gonna say this dp of L and R. So what this value is for the left and the right. See, that's interesting. So when we get the dp of L plus 1 R, we add that left side, which is this one. That we add signums of L, which is exactly I plus 1. And similarly, this is on the right side, is this other dp, this is the right. And that's that j minus I plus 1, or excuse me, j minus 1 plus I. That's the right side. Yeah, we take the sign of each of those, and then we say, depending on the sign, if sign is greater than 0, then we're going to update. This depends on the select left and select right, so it's going to be maximum of select left, select right, and then this is the other way around, otherwise. Okay, this is my solution encoded in a vector, or yeah, bottom-up dynamic programming style. At the end of it, you're going to return whether that's greater than or equal to 0. Whew. Does this compile? Start with that. Okay. Let's comment out the rest of this. I think I greatly prefer this first approach. The second approach is kind of a mess. It's fun, but it's something of a mess. Oh, it's correct. Okay. It's correct on some other cases. All right, let's try those. Let's try some things. False, or wrong rather. Incorrect. No, no. Trying to encode this this algorithm with the This is so funny though. This is like, come on. Ah, okay. Oh, that's why. The sign's supposed to flip each time. That's why. And toggle the sign. Alright, how about that? What does that look like? Wow, looks correct. Alright, let's go for it. See if that's correct. We'll find out shortly, soon enough. Wrong. Nice. How did I miss that this case? Probably should have thought about that. Okay. Which one's incorrect? The bottom three. Okay. So the bottom three gives us one and 100. Wait, why is this wrong though? If the sign, it's n modulo 2. So if it's odd, it means the last thing that's, if it's odd, it means the second player will finish, right? So if you have one element, no, if it's odd, it means the first player is going to finish, right? First player goes, second player goes, first player goes. Oh yeah, this is wrong. Am I right? Am I wrong? Why, Wait, but then those are all wrong. Wait, how did I get this, mix this up? That doesn't seem right. So it, Am I supposed to do the negation of the sign afterwards? Is that why? Maybe that's why. Maybe it's supposed to come after. I mean, still, how do we do that? Does that work? No. I'm very confused. Oh, 1, 2, 3, 4, 5, 6. Wrong. Okay. If there's 3 elements, that means the first player, so it's odd. Yeah, this is what it's supposed to be. If it's odd, the first player finishes. Yes, correct. If it's odd, the first player finishes. So 1, the first player takes the first one. That's it. He wins. If it's 3, the first player takes something. Second player takes something. First player takes something. So yeah, if it's odd, the first player finishes. So you add n mod 2. If it's even, we'll give you equals 0, be even. Excuse me. So we just do. Let's do this. N and 1, right? If it's even, then this is false, and we get -1. If it's odd, then we get 1. Okay. Now we've already established this this part here. So now we need to do sign equals negative sign times 1 before we do the rest here. We don't need this part. So this should be correct, but now that's, I think, the thing we're getting stuck on. So this is wrong somehow. So why are these wrong? It's like just the first one is wrong. 152, wrong. Okay. How are all of these correct, but this one is wrong? Need more test cases. Yeah, interesting. No. No. So if the sign is greater than 0, that means it's a 1. So I want to say that this is supposed to be reversed. Oh, okay. Is this... Oh, this is wrong, actually. So left plus 1 minus 1 is what's here. Right minus 1 plus 1 is what's over here. Oh, that's why. Yeah, that would have taken me forever to figure that out. Oh no. I think this is fine. The last thing you add, on the left side we said it's I plus 1, j plus 1, or I plus 1, j plus I is just I on the left here. Right? And then this is left and right minus 1. I don't know if these are exactly correct either. What values are these? What numbers are these? Yeah, I don't know how this translates to the left and the right values. Well, it does. I actually do know. This expression, this is the left and right. When you call those functions, you're actually using the left and the right of this. Yeah, so the 0, 1 is actually what we're supposed to use. So the left part is this I, and the right part is j plus I. So that's correct. That's left and right. Add the dp appropriately, which is left, you get I plus 1, and right is minus 1. So that's correct. And then it says if toggle, select left, select right, maximum. Oh, these are both max. How did that happen? I thought I missed something important, man. I was like, there's something here that's not right. Oh, here we go. Okay. Wow. Let's go for it. Yeah, I need to do more testing on that one. Oh, hey, we got there. Sweet, 100%. Hey, hey. Cool. This is I'm actually not gonna remove this because this is like way too complicated. This is kind of insane. Yeah, man. This was a lot of fun. I don't know if I'm glad I did this. I don't know how I feel about this. But it took us 4 hours. We're at this now, 3.5 hours. I think I need to go eat some food and go to sleep now. I don't know I don't know how I feel about this. I don't know if this is good. This is like, this seems kind of bad, actually. This probably fits the category of bad. This is probably just bad. You actually could use even less memory than this. You have to translate this somehow to, like, I don't know, make this one array, and then this is the next array, and then this is the next array, and this is the next array, and this is the next array. Yeah, there's like a translation you can do of some kind, a way to view it correctly, where yeah, I try to just get it correct, just so that was at least right. So it was just sort of the dynamic bottom up equivalent of this top down approach. But actually, it's really complicated because of how these values are related to each other. There is such a thing as like setting this to be the row, and then each of the values that come after is like the next row. You just have to get the relationship correct between these. Like this is actually index. This would be like, or you could do 0, 0 for this row. But then this is 1, 0. I guess the row would be a 1. And then all these things you add a 1. So they're actually related to, what do they relate to though? That's the thing that's confusing. This would also sort of be like the first element of the row, of the next row. At least the index is the same on this part. So you could do it that way. So this would be like J, I guess, is the row, and then I is the column. Or you'd probably want to do I as the row, and then J is the column. So then you'd have something like this going down, where this is I is the row from 0, 1, 2, 3, 4, and then J would be these values, right? These columns from 0, 1, 2, 3, and so this point here you would sort of have to add 1, or add J to it, or I rather, add I to get this translated value, so that the L and R in this case would be translated to, the L's would be, actually the L's would be the I values, or the J values, and the R's would be the L, I think it's L plus, or I plus J. Yeah, R would be I plus J. And so then when you DP, it's going to be it's going to be DP of, it looks like 0, 1 would actually be, it's I is the row, and J is the column. So J is looping from 0 to, it looks like, n minus I, and then I is looping from 0 to n minus 1 minus I, and then I is looping from 0 to n minus 1, and then and then this is going to be related to so the right side would be one row before, and the column is the same column, and then the left side is one row before also, but increment the column. We said J is n minus I minus 1, so that'll always exist. And then you're going to add the left and the right. Now to figure out the left and the right, we said L is j and whatever this L is on the DP, you subtract 1. Yeah, well, that's confusing. It's technically L, yeah, L minus 1. So this is nums of L minus 1, which is J. And then this is nums of R plus 1, which is I plus J plus 1. R plus 1. That's if you translate all these variables. That way, it's like just a simple row, bottom up, row by row. I almost had something like this. I was getting pretty close. I was like J and J minus 1, and I was just or J and J plus 1, and I was getting so confused. Because I was like, there's no way that you just add nums of I and nums of J or nums of J minus 1 or whatever it was I was trying to add, and I was correct. It was not. It was it's kind of complicated, the translation of what you actually add each of those numbers. It's not that complicated. We can actually write this and see if this works too. This is if you transform this now. So let's actually copy this and try it again. Dude, it's really involved. It's really involved. Yeah, so same deal. Sign is the same. Instead of I, we're gonna do I is 0 and loop over all of these values. And now we're going to say, oh, and by the way, at the end of this, it's I at the top and J of 0 now. So I of n minus 1 and J of 0. So slight change of how this is going to work. So now we said this is the left selection is J minus 1. Excuse me. I is now looping over, we're going to put I up here. I loops from 0 to n minus 1, or in this case 1, n minus 1. Excuse me. You have J from 0 to n minus I minus 1, which is just less than n minus I, plus J. And then you're going to say, yeah, select left, nums of J minus 1. And then right is going to be I plus J plus 1. Just like, okay. And then these DPs are, it's the row behind you. However, one of these J stays the same, the other one J increases. So the left element J stays the same, the right element J increases. And there you go. This is what we were going to do before. And that's pretty much it. Yeah. And it's just DP of now. Oh, what's interesting is that this just loops from I to J, by the way, or from J to I. Just loops over J. Right, and we have the min and the max. Select left, select right. Greater than or equal to 0. Let's see how that works. If that works. Runtime error. Nice. Addition of unsigned offset overflowed. No. Excuse me? No. What do you mean? What do you mean? Oh, I see. You can't do J minus 1 anymore, though. Ah, interesting. Okay. That's not the left anymore. J? Yeah. Well, let's loop it. Yeah, it loops over. Actually, the choosing the right side, J doesn't change. Choosing the left side, J increments by 1. It's so confusing. It's actually just J. Not J plus 1, it's just J. Or J minus 1. The left side, it's just J. And then the right side is you actually decrement the, so I is the row. You would decrement the row plus J. Hold on. Yeah, it's actually I plus J because it's the row plus J gives you that right value as J loops from 0 to n minus 1. And then you actually decrement it by 1 because you want 1 less than, it's row plus J plus 1 is this, well no, yeah, it's just I just apply plus J, yeah, it's this right value. So I plus J. No, come on, shoot. That's not overflowing, but it's correct. And then the values that we depend on are previous row, both of them, I minus 1, I minus 1, and what's the J values? 0 for this guy, right? It's just the previous guy on the right. The right is J, the left is plus 1. Yeah, okay, I had that mixed up. I think that's it. Hopefully, maybe. Ah, there we go. Nice. Let's go for it. See how we do. If it's correct, yeah, there we go. Okay. That's another way of doing it. Translated slightly. Still really confusing, but go figure. So selecting the right side would be dp of I minus 1j plus I plus j. How, why is that? I don't know. And selecting the left side is also previous, but it's j plus 1 and then j. Yeah, that's extremely confusing. Yeah. Let's think about that for a minute. Like if I saw this code, I would just be like, this is gibberish. Like this is just, it's not even real. Who wrote this? Why'd they do that? But if I understood that there was actually this program translated into a DP solution, bottom-up DP solution, then it makes a lot more sense. Extremely unclear bottom-up solution. DP solution. Yeah, that's great. That is fantastic. So what I was thinking about is like putting in some kind of the reason why you might want to do this, and it's because it's kind of hard to get. Like you might want to allocate the memory first for this memoization function, and then use the memoization, and then use a matrix instead of a hash map, or a what do they call that map? A hash map, or the other one is a instead of a hash map, or the other one is a regular map, a tree map, hash map or tree map. Instead of a hash map or a tree map, you can allocate the memory directly to get your hash map, to get a vector. But the problem is that, like, setting values, you want to be able to check whether or not you've already set the value, and you want you kind of need like a sentinel value to do that, which limits the range of integers you can operate on. So you need to know your range in order to do this properly. You could do it here. You could do negative, like the most negative number to use that. But because you can see in the hash map you have like if this has been set already, then reuse it. But if it hasn't been set, then you would set it. So that's kind of the deal. You need the ability to check whether or not you've actually covered this value. Whereas here, I mean, you just you won't even touch it unless it's already been decided. So it's pretty interesting. You kind of already have done all of the previous values. You sort of do row by row, so you can guarantee not only they're always there, but they will have been set already. Yeah, they already have been set. So that's kind of why you'd want to do it this way rather than this way. The tree approach, like, yeah, you do sort of a depth first search. So it actually, you don't necessarily have all the values you need once you look at that node. You have to traverse the rest of the tree, whereas here you basically take the tree and make rows out of each layer of the tree, and then you kind of work upwards. That's pretty much what the bottom-up version of it's pretty much what a bottom-up DP solution of a tree-based memoized DP solution is. This is a lot more efficient because you can allocate all the memory in one shot, and you do a lot less, I guess. You don't really use the stack at all. You have loops, so those loops can be optimized and unrolled and things of that nature. Excuse me. And you also don't require any hashing or a tree map or hashing or all that. All that extra overhead to use those data structures is not necessary either. So you kind of like, it's interesting is a lot of solutions have dynamic programming versions of them where you do a suboptimal exponential time algorithm, then you can memoize it to make it an asymptotically optimal dynamic programming solution that's a top-down memoized version. And then I think you can prove that any top-down memoized dynamic programming solution has a bottom-up dynamic programming solution doesn't have to be memoized because it's just an array of values that you're setting. And I think that's what I was getting stuck on the other day. Like I was looking at that idea, and I was looking at like basically difficult dynamic programming, like dynamic programming solutions that are kind of difficult to understand, but like you can do them. That like the equivalent top-down memoized version is actually like hard to understand or to write, I guess, something like that. Sort of going from one to the other. I think you can always go from one to the other, but it's just challenging to kind of figure out exactly how to do that. Yeah, this is definitely a really interesting question. Pretty wild. I don't know. Part of me thought initially that you could only do this using an exponential time algorithm. I didn't actually realize or think that you could do this using either dynamic programming or memoization. And yeah, I went from like, O of n to the fourth memoized solution to to a quadratic time dynamic programming solution. So that's pretty good. Oh, interesting also is you don't need quadratics. You don't need this whole vector. That's actually another optimization here that we're missing. You can do just standard vector of int, so just say previous. We'll do it this way. So now we can say previous of I, which is going to be n0, signum is num, and then you can say both of these. Yeah, you don't actually need the whole array either, by the way. Instead of nums, you can do previous of j. Oh no, excuse me. That's fine. That's the same. It's dp of I minus 1 is just previous. So anywhere, yeah. So some like once you've actually resolved your dp solution to be bottom up and you're going just vector by vector, you actually don't necessarily need more memory than a single vector. So which is what we're going to do here. So anywhere you see dp I minus 1, that could just be a previous vector, and that's fine, and you're in good shape. And so now what we're going to do is standard vector of int. We're going to call this a new v, and it could be actually, this doesn't need to be size n. This could get smaller and smaller as you go. Really, this will end up being previous of 0. And we're going to say not n. It's actually n minus I want to say. Yeah, it's n minus I. We'll do new v of dp of j. And then all you need to do is, once you're done, set previous equal to new v. Try that one. Give that one a shot. See how that goes. Oh, wrong answer. Nice. I gotta back up here. I think this is previous of I, not previous of j, by the way. Oh no, j is the inner loop. Okay, no, that's fine. Oh. Alright, let's see how this works. Wrong. Why though? A lot of these are wrong. So, interesting. Previous n0. Previous of I is signums I. This is the next row. Okay, n minus I, j, select left is basically the same thing, except previous of j plus 1. and previous of j. This is right. It's the same. Sign is greater than 0. We say, oh, it's not previous anymore. It's new v. Excuse me. And then after we set all of those values, we set previous equal to new v. Okay, how about that? Wrong. Shoot. Shoot! Also, it looks like it's slower because we're allocating memory each time, I guess. Only really need 2 arrays. Don't need to reallocate this array every time. Definitely not. Why is this wrong though? It's very similar to what it was. So we take our previous values, perform our calculations, set our new values, and then set our previous to new. We can move it. Allocate memory again each time. But this is still wrong. At least it's faster. But yeah, still wrong. Why though? Oh! That's why. I think. Hey, there we go. Let's see if we're correct. Hey! It's a little bit less memory it's used. Though this is a linear amount of memory. Now, not exactly though, because we're allocating this over and over, which seems kind of bad. We can do slightly better than that. We can do new v of n0, and then we don't need to do this each time. We can just copy these values over. So previous, we have new, and we write all these new values to the new v from previous, and then we set previous to the new, and we just kind of keep doing that over and over again. I think this should be a little bit slower, but I'm not sure if it really matters. Yeah, oh, okay. Just a little bit less memory, I guess. But yeah, so that's linear in the memory too, so we don't need to use that much memory. I don't know if this is the best way to do this. Feels like this is a reasonable way to do it though. Yeah, so we should actually get rid of this. So that's one of the upsides to that's a better, this might be the best solution. Let me see. So this is like, I want to say there's like probably a theorem or something that, whoa, what happened? Did I slow down? Some cases were 7 milliseconds, some cases were 0 milliseconds. Okay. I want to say this is a solution where or this is a kind of problem. This is a solution where, and I think this is like a theorem in general. I want to say the optimal for a top-down recursive solution that has some overlapping solutions, so you can use dynamic programming to bring the solution from something that would be otherwise be sort of exponential time to polynomial time, and also have use some memory to do that. In those situations, it looks like even if you, well, actually, the memoization will automatically give you the optimal memory bounds. It'll be slower and it'll use a significant amount of memory just because you're going over a lot of different, I guess, possibilities. But you kind of get things somewhat automatically because it's hashed. So you'll actually automatically get the optimal memory bound because you're only going to end up using as much memory as needed. No, excuse me, I take that back. No, wrong. You get the worst memory bound. Yeah, I'm sorry, I take that back. You get the worst memory bound because you would use quadratic. You would have memory for the entire tree. You have to have memory for the entire tree. Right, I take that back. It's the it's a bottom-up approach where you would not be required to have the memory for the entire tree. You only need memory for the section of the tree that, because you're sort of doing a level order traversal of the tree. You only need enough memory for one level of the tree at a time, which is linear, rather than, or in this case, would be linear. Now you could imagine similar solutions where you'd have like pyramids, or like, I don't know, the fourth dimensional version where you have sort of multiple instances of a three-dimensional thing going on. It's like a four-dimensional dynamic programming solution. In that case, you have one dimension less of memory required. You would only need to keep that three-dimensional portion that changes each time. Right? You sort of have like a three-dimensional piece, and then you have another three-dimensional piece that you evaluate from the previous one, and then you could toss the previous one, and you can sort of always guarantee one memory, I guess, one, what do you call that? One exponent less of memory, which is a lot. I mean, that's a lot. That's pretty interesting. Something to consider. I don't know. That's like, yeah, you could probably write a theorem somehow with that, a generalized kind of thing. But yeah. Anyway, okay, pretty interesting. Let's go. I don't know what to say about this problem other than just pretty interesting problem. Grateful that we did it. I need to eat. Yeah, I mean, we didn't get anywhere near the DP originally. Like we were so far off. But this is pretty interesting. I mean, there's a few optimizations you can make here, quite a few, to bring this to better speed and better memory. Thinking if there's anything else I want to say here. That's it. All right. Thank you for watching. Talk to you soon. Have a good rest of your day. And that'll be it for today. I don't know what I'm going to do tomorrow. I have, I don't know, just keep going one day at a time. So yeah, take care. Talk to you soon. Bye.